I'm going to introduce the next speaker, who's Deirdre Shoemaker. She got her PhD from the University of Texas at Austin. She was a postdoc at Penn State and also at Cornell, where I got to know her pretty well. And her field is numerical relativity and relativistic astrophysics. And she's currently at University of Georgia Tech, the real place, right, in that part of the world, right? And one of the co-founders of the, I won't get the title right, but the Center for Gravitational Physics there, right?
Good enough.
So, thank you, Deirdre.
I should name the center as partially your fault. Yeah, because I was asking you for advice before we moved to Georgia Tech, and we made it too long. It's too many syllables. The Center for Relativistic Astrophysics. So if you ever have to name a center, fewer syllables is better, just for people's memories. So thank you for the invitation, gentlemen, I think, because I started out really gung-ho, and then I realized quite quickly that I couldn't do justice to all the work that's happened in this field. So people in the audience would probably notice things I've missed. I think it would be great if you felt like you could contribute, if it's something important, because I know I've missed many, many important contributions. So I attempted to give a feeling of where are we in this moment in the last few years on the way we theoretically predict the sources to provide information for that famous match filtering, and sort of where I think we need some work over the next few years. So let's start with this now, I think, famous figure. In fact, I think it exists in both documents that Kurt talked about. I usually took figures from the document on the right, which was the Lisa L3 document, but I think it's in both, including the Gravitational-Wave universe. So there's a lot of, I'm trying to make myself stay here. There's a lot of sources here that Kurt covered all of them, and I'm not going to cover all of them. That was the first cut I made. I'm going to focus on binary sources that are not white dwarfs. Sorry, I know one person's noise is another person's source, but I'm going to ignore them. I'm also going to ignore the emeries. So we're going to focus on these supermassive black hole binaries. And the thing that I want to point out here is if you watch these tracks come by, what's crucial is that depending on the mass, the total mass of the binary from 10 to the 5th, or even down here, just a few hundred to 1,000 solar masses, up to the total mass of 10 to the 7th, you're really talking about a different way that we would think of looking for these sources. What type of approximation or solution to Einstein's equations, which governs the binary black hole source, what is the best way to get at the physics that's happening, the physical parameters of these sources? So when you have something sitting here for a year to months, it would be silly to use the full power of numerical relativity, which I'll describe in a second, solving Einstein's equations when they're full, to go after something that is well approximated by PostAtonia. And as you get up to a lower mass and you have maybe less time, or when you're looking at this merger, so what's happening here, as Kurt described, is you have the in-spiral, a merger, that's where things are very nonlinear, and then you ring down to a single expected Kerr black hole. So I'm going to talk about the ways that we approach getting at every piece of that signal as we go on. So the other important thing on this plot, I think the takeaway message is understanding how things change as they evolve across the Lisa band, depending on the total mass of the binary. So I grabbed this wholesale out of the L3 document because, unlike many of the people in this room, I sort of ignored Lisa for a while. I'm one of those people that buys clothes in season. I like to wear it right away, and I don't like to plan. So I just couldn't focus on it when it was too far away. It's still a little too far away, but nonetheless, I feel like now is the moment, especially in the United States over the next couple of years, where we sort of make the case again and bring the excitement up. So I've gone a little more all in this time around. So I've been studying that L3 document, and it's very well written in the sense that it has it's not very long, but it gives you the sense of the inspiration you need to understand what science you're going after, and then the nitty-gritty details that say this is what you have to achieve to make it happen, to say Lisa was a success. And I'm sort of focused on those, what are those little nitty-gritty details, even though I don't put a lot of them in here, because if we are going to provide the waveforms that are going to allow us to get the physics out of these sources, that's the kind of thing we have to pay attention to and make sure we can do although we have a couple years, so we're probably right. So these SOs, if I understand correctly, it's very jargony, are the science objectives, and the SIs are the science investigations. Don't ask me what the difference is. We need a person who understands Lisa a little bit better. But the point is, I'm going to focus on these sources that are 10 to the 3 to 10 to the 7 solar masses, these binaries, and that's their total mass. And there's a lot of beautiful science you can do, as Kurt already mentioned, quite a few of them. I just picked out some of the ones that caught my attention. So one of them is to trace the origin, growth, and merger history of massive black holes across cosmic ages. Sounds simple, right? I mean, it's amazing to talk about these binary black holes throughout all cosmic time. So that's sort of the big objective, and you can get down into some more details. Study growth mechanisms of these massive black holes from the earliest quasars. So what this starts to do, by saying that this is something you want to achieve, it means if you're providing the theoretical underpinnings, that we have to be able to measure dimensional spin parameters to 0.1 and misalignment of that black hole spin to 10 degrees. So this puts restrictions. You have to have a waveform that's accurate enough that when you combine that with the data analysis and the noise of Lisa, that that's achievable. Another fun one that Kurt mentioned is observe the electromagnetic counterparts to merging binary black holes. So one of the things I included in here and was asked to include are what we call wet binaries. So dry binaries mean we're only worrying about the binary black holes and the gravitational wave signal that's produced. And a wet binary means we put in the environment in which these binaries might exist. Accretion disks, gaseous clouds, something along those lines that would produce the electromagnetic counterpart. As I was sitting there listening to Kurt talk about how a lot of the astronomy will come from here, I was also thinking about that the binary neutron star that happened with LIGO, it was exciting, especially because everything happened in the moment. So the neutron star came with gravitational waves, the gamma rays. I mean, radio are the slowest because they're still, I don't even know if it's peaked yet. Does anyone know if that radio is still going up, right? So it's amazing how much slower, right, the radio emission takes for these. But with Lisa, we're talking about months to years. And it could also be that we're going to end up with a collection of sources of population in which the electromagnetic information need not have to happen at the same time as the gravitational wave, right? That we will understand populations in a way that we'll be able to classify the EM counterparts from different epochs that the source might go through throughout its life. Another one was to test the existence of intermediate mass black holes. I like this one because it's one of the things my group does with LIGO is to search for these intermediate mass black holes, ones that are a little too massive, a few hundred solar masses to 1,000. So that one intrigues me to see it also from the Lisa side. The origins of stellar mass black holes, so this is what we were just talking about with the multiband gravitational wave astronomy. How did these sort of fat stellar mass black holes happen? And then using ringdown oops, sorry, that was typo. From merging black holes to test if those final black holes that we see in band are really Einsteinian. Are they the curved black holes we expect? We were just chatting about this. Now, when Kurt was talking about it, most of that came from the Emery point of view. The Emery point of view, you get these exquisite maps of what's happening as something falls into a big supermassive black hole. I'm looking at it from the point of view that we do see the ringdown coming from after comparable mass black holes have merged together. And that's another test of what it looks like for the black holes to lose hair. So we have both of those potentials in this detector. And everything I'll talk about will be comparable mass black holes in contrast to Emery's. So here's another fun plot from that same document. And this one I like because it shows you how, I want to say insane, that's not the word, how exciting it is to get the full redshift and mass range, right? This is quite the promise that this detection has. And on this side is the luminosity distance, because everything can be redshifted. So the little red stars here are these threshold binaries. And if I understand correctly, and please correct me if I'm wrong, these are the things that we say, all right, we need to be able to detect these. It's be the minimum requirement we want to place on our models and the data. So you can see it goes out to z equals 20. And right here, this is where we've been talking about the sweet spot of these binary black holes for Lisa. You can get the larger ones, but you're not getting them as far away in any sense as you do the more canonical supermassive black holes. All right, so that's what we're going to talk about now, is dive into how we create these sources. I pulled this out of Ed Porter's summary paper he has on the archive. Thought it was a nice, quick summary of some of the sources of Lisa. And just to put it in context, I grabbed some here, but we already kind of talked about this. So we're talking about an event rate of about 100 a year. They're very luminous in gravitational waves. Even if you forget about the electromagnetic counterparts, we're talking about 10 to the 6th compared to the times the solar luminosity. And the potential of the parameters is huge. So what we're really after at the end of the day is to understand the parameters of these sources and the environments they grow up in. And so one of the things we have to keep our eye on when we talk about how expensive all these simulations are that we do is how accurate we're going to be able to get at the components, the luminosity distance, time of merger, and many other pieces of information like spin. So that's just to keep our eye on. So here's my cartoon of solving the Einstein's equations. So they're either the very pretty equation that looks almost meaningless, but you know, the famous equation of Einstein G mu nu equals T mu nu. And by the time most of us get done with them, it's a very ugly mess on the right-hand side of many derivatives, a lot of choices, etc. And usually we don't talk too much about what's happening under that hood because it's a bit ugly. I won't talk about it here, but there are many sources to get at a sort of more introduction to both general relativity, PostAtonia, numerical relativity, etc. And the point is really that what we're after is to explain this, to predict this gravitational waveform coming from these binary black holes. And as Kurt said, you could use the quadrupole formula, and if they're really far apart, we could even go back to Newton and Kepler. But what we're worrying about now is when we actually get this merger and ringdown in bands, we're looking at this long, full history of this binary black hole source. And another thing to look at is that if you look at these time scales and study how the energy is radiated of the binary as you go across time, this time is in units that are meaningless because we can scale the total mass of the binary. So it just means that you're starting from whenever it starts to have gravitational wave emission take over until it merges, and then it will ring down, and you can see how that energy radiation increases in time until you get to the merger. So I'm going to try to pull this completely apart. Since at the lower total mass binaries, you're going to have this long and spiral. And as we increase the mass range, you will see these merger ring downs in the Lisa band. So let's talk about how you get them all. So this is what I call anatomy of a black hole. It comes in 3 parts in spiral, which is well described by the PostAtonia approximation to general relativity. At some point, as the black holes, the fact that they're not point masses and the fact they're moving too quickly with respect to the speed of light breaks down the PostAtonia approximation. Where that happens will depend on the PostAtonia approximation and also the physical parameters and the accuracy at which you're trying to measure or the precision. So that's a little bit complicated right there. And at some point, numerical relativity takes over to do the nonlinear portion, the merger. There's the only approximation in numerical relativity is that you have put the equations, Einstein's equations, on a computer, so you're at the mercy of how well you've truncated the solutions. It's now a discrete solution instead of finite, and you make some decisions on initial data and stuff, and I'll talk about that in a second. And then you get to ring down and eventually perturbation theory, where you very well understand how a final black hole steadies down to its final state. So we go from a situation with a lot of parameters down to typically called 2, the final mass and spin. And this is just because when we talk about numerical relativity, we usually work in this thing called psi4, but it's just 2 time derivatives of the strain. So they're closely related to each other. I'll talk mostly in strain, but that was in case I made a mistake. This is one of my favorite pictures from Bonanno and Satya Prakash, because if you know Alessandro, it makes sense that the effective one-body model covers the entire space. So that always just cracks me up. I know I'm being recorded, so it's really good work. It just cracks me up. So this is, we're looking at the landscape. Now, instead of looking at a single waveform from 2 black holes colliding in time, we want to look at it in terms of parameters that governs the physical space. So here is the mass ratio. So if we go, I'm usually in this world, more comparable mass, because I sit around here. And this would get to emeries. So here, when we get to really strong mass ratios, as Kurt mentioned, we're in perturbation theory. And when you get to far separations, you're in PostAtonia. So we have sort of well-defined epochs of PostAtonia, perturbation theory, and numerical relativity to cover this full space. And then there's a lot of work being done to blend the boundaries, especially here, less so here, but effective one body also works in that direction. So I'm going to talk about all of these pieces, except I won't talk too much on this side. As Kurt said, I'll talk about these pieces in here as we go forward. I went back to this. I don't remember why now. I had a reason why I did that, but I think Kurt described things well enough that I don't feel the need anymore. So I'm just focusing on how we combine all three so we get that full signal depending on our mass. This is for fun. So I told Larry earlier I don't really know PostAtonia. I put my head in the sand when it comes to PostAtonia. I think it's those fractions people always show, which is too big, so I usually ignore it. But nonetheless, we could talk about it in a moment. So I try to pull out enough information without making anyone go crazy so that we have some context to talk about the advances in PostAtonian theory. So PostAtonian theory is this expansion in V over C at some level, as Kurt talked about. So advances keep being made that you get higher and higher order corrections so you can cover more physics with the PostAtonian approximation to the full Einstein's equations. So this is the typical way that we already seen. We're going to talk about the strain in terms of two polarizations, plus and cross, and these are the intended patterns of the detector. And this is assuming a very simple two orthogonal detectors for LISA. So if we want to write down the 2pn approximation of these H plus and cross polarizations, it would look like something just depending on this symmetric mass ratio. So that thing just depends on the two individual masses of the black holes. And then here you have the terms that we're talking about. What order Pn you're talking about depends on how many of these terms you've calculated out. And this parameter x is related to the frequency. And so and here it is divided by the luminosity distance. So you can imagine continuing to add terms as you go higher order of PostAtonian correction. And then we can also talk about the orbital phase and the orbital frequency. The frequency is just the orbital phase divided by the time derivative of the orbital phase. And so now you can get at the frequency as well, and then just like before, you will have these corrections to the phase. So these are the two pieces we're going to think about as we go into PostAtonian. And now this is where it's at. So Luc Blanchet very recently, 2016, did a complete, as far as I can tell, description of PostAtonian. It's a very nice summary of the work. He includes this table, which you can't see all these. These are references to all the pieces of work that have been happening. It's quite the tour de force. So you can see how people have been working very hard to keep going in the PostAtonian approximation, increasing what's covered in the approximation to spin squared and tidal terms in many different ways, including the amplitude of the waveform and its phase. And so I thought it best to really push people towards that Blanchet summary. If you want to know more about PostAtonia, he talks about all the different things. It's a really nice, long, but nice paper. And also the Bonanno and Satya Prakash paper of 2014. I wanted to focus us in a different direction, because I think one of the things that we have to pay attention to at this moment is what's the physics we see LISA can do, and sort of where are we in understanding all these terms so we can get at those physical parameters. So I would sort of call this the state of the art of in-spiral waveforms. So we don't worry about merger and ringdown, because most of the time these binaries are going to spend in the LISA detector, they will be in-spiraling and describable by PostAtonian. And there's been an amazing amount of work being done, and this does not cover it in any sense of the word, in getting these in-spiral waveforms built off of PostAtonian approximations ready for LISA. So it starts way back, 1998, that wasn't that long ago, was it? No. With the Newtonian quadrupole, and it builds from there, right? And you can see a lot of these people are in this room. And getting more the spin-induced precession, simple precession, adding higher harmonics more recently, worrying about eccentric waveforms. So what's happening here is that people are adding more and more physics, or covering more and more physics with these in-spiral waveforms, because at the end, we want to be able to, you'll probably detect them no matter what, but you want to be able to get all the physics you can out from these LISA detections. And so you want to be able to understand how the higher harmonics come into play, how eccentricity does, spin orbit precession, the whole thing. So there's been a tour de force of work going on. And you can sort of see a jump. I think we're all busy from 2008 to 2014. There's probably papers I've missed, and I apologize for that. But at least it will get you started to understand all the work that's been happening on the in-spiral waveforms and how more and more physics has been added. I don't know if anyone can say in this room, maybe you can, that there's a definitive, we definitely can get all the physics we need out of in-spiral waveforms, but I have a feeling things are still working to get all of the different physics in place. So the thing I feel a little bit more comfortable talking about is building these in-spiral ringdown, merger ringdown waveforms, because it's closer to my own world. So this is talking about trying to now get at the sort of middle and end of that binary black hole thing and make sure we can capture all the physics there. And the delicate part about this work is that you have to sort of work at the boundaries of both Post-Newtonian and numerical relativity and the numerical relativity and perturbation theory. So that's the tricky bit about this work. I like this slide. Half the people in this audience have seen this joke already, but it still amuses me, so I share it every time. Because I think that this idea of people taking beautiful sort of records of what happened in conferences years ago is fun, and this was 1957, so it usually kind of wins. This is the first time numerical relativity was mentioned. I don't know if that's true, but that's what I have, the first time I've seen it. So this was Charlie Misner summarizing the discussion of the first GR1 conference that happened at University of North Carolina, Chapel Hill. And they called it, they were talking about how we're going to solve the two-body problem. So it was first we assume that you have a computing machine, which I also love calling it a computing machine, better than anything we have now, and many programmers and a lot of money. We still want that. We don't get always a lot of money. And you want to look at nice, pretty solutions of Einstein's equations. So what he's pointing out is the hard part of doing initial conditions. And he's worrying that either the programmer will shoot himself or the machine will blow up. And the good news is, while that was a problem, not the shooting yourself, I don't know of any of that had happened in numerical relativity, but the machine did blow up. Not completely, nothing was on fire, but for many, many years, famously or infamously, it was very hard to solve this problem in full numerical relativity with Einstein's equations until about 2005 when Pretorius made his breakthrough, and soon after when RIT and NASA followed. So what this means is we have the potential to solve the two-body problem in general relativity. This is without any matter. This is just two black holes. So finally that barrier was broken. And sometimes I put the joke in here also of Saul Tarkowski and Stu Shapiro calling it the Holy Grail, which is, I think, a mistake, right? So once you have a Holy Grail, it's going to take you a long time to solve it. But it's okay. It happened. So numerical relativity is going to be important whenever you have these point masses that are now black holes. Their physical extent is no longer suitable to call them a point mass, and when they're moving too quickly. So PostAtonia begins to break down, and numerical relativity takes over. And this is a computational challenge, right? So you're literally solving a system of PDEs that are coupled and nonlinear, and it's a boundary value problem. So you specify initial data, and then Einstein's equations will solve that data forward in time, and you get out not only the geometry of the space-time, you get out the dynamics of the black holes and the gravitational waveforms, which is what we're after. So this is a pretty old slide, so you can see nothing's really moved past 2012, but I wanted to give you a sense for what it takes. And so if you ask what do we usually worry about in numerical relativity, it's specifying good initial data. Jeffrey Lovelace, who's here, has worked on extreme spins for a long time. This has been less worked out, which is extreme mass ratio, which means getting closer to perturbation theory. I think we're pretty weak here. I don't remember what the mass ratio was in this one. The Lusta paper, they did do a 1 to 100, but they didn't produce gravitational waveforms for it. The evolution equations, there's about 3 different styles. One is here at Caltech and Cornell, the SXX collaboration. Another big one is the Einstein Toolkit, which Georgia Tech, RIT, LSU, and several others use. And then there's another code in Europe led by Bernd Bruggen called BAM. So the good news is there's different codes, and we all can work together to agree on things and make sure that the physics we're producing is solid. Here's the problem, though, is that they still take a long time to go. And weeks to months of compute time, depending on the number of orbits you desire and the precision you want. And the problem here is that with LISA, you sure do get a lot of orbits. So clearly there's going to be a lot of work to combine in-spiral waveforms with these numerical relativity waveforms, and I'll give you a summary of how that's been done recently, although most of it's been done for LIGO-like sources. And then, of course, we have to extract the radiation from our codes. So this diagram is just to show you the initial data. We often talk about these spins of the black holes and their masses. So these spin vectors, in principle, can be pointing in any direction. We want to know that information because it will tell us about how these binaries formed, whether or not these spins are aligned with the orbital angular momentum or not. All this information could be very valuable, including the magnitude of these spins, to understand the history of these binary black holes. So Finally, it happened, and I love this Kip Thorne picture because we always laugh that it doesn't look like that. It's very smooth and kind of boring. It still takes a long time to solve them, even if it's smooth and boring. So, we had a lot of work that had to make this possible, including mathematical tools like gauges. What that means is that the problem with general relativity, if you teach it, right, in class, is that we don't have a background in which our fields propagate. We have to solve for the geometry and the fields at the same time. And so we have, when we do numerical activity, actually our coordinates are evolving in time. And we solve partial differential equations for our coordinates. So it makes things complicated to get the geometry out at the same time as the physics. And of course, it takes a lot of computational infrastructure. So I point that out, and I have a slide that just pulls this out a little bit for one of the codes, because we're paying attention to how much compute time it's going to take us to get these waveforms ready to go for LISA. So we did a lot of work. It was fun. And now we get to play in the Gravitational-Wave playground. So if you're looking at where you can find numerical relativity waveforms, there's currently 3 catalogs open to the public. Ours, SXX here, and Cornell, and let's see, CETA, and a lot of other institutions, and RIT has opened one recently as well. So what these catalogs provide you is literally strain waveforms or psi4 waveforms as a function of time, depending on the initial parameters of the system. So if you specify the 2 masses, the 2 spins of the initial black holes, then you will be able to find which waveforms cover that. The caveat is that the longest ones, the most cycles covered, are typically found in the SXX catalog. Ours are shorter, so it also depends on the number of orbits you're expecting and the precision. But this is where you can find at least some. At this point, there's got to be close to 1,000 waveforms available. Some of them overlap, which can be a good thing. Another thing to pay attention to here, as we talk about computational challenges, is that for each, I don't know about these two, for each one of ours, we don't always have a convergence test. And what a convergence test means is that you run the code at multiple resolutions because you want to be able to put error bars on how well you're solving Einstein's equations and how much you can trust the waveforms. And that takes a very, very long time, computationally speaking, and a lot of computer power. So not every single waveform of ours, I know for sure, has a convergence test. So there's a lot of behind the thing here behind the screen of amount of computational time it takes to get each one of these waveforms. And the problem is it's very boring work, if I'm honest, right? Someone has to sit there on the computer, set up these parameters, let it sit weeks for a long time on some supercomputer somewhere, and pull it all back together. So it can be a slow slog. I wanted to pull out this old gem because I think it's important for us also to pay attention to how many cycles can we produce reliably in numerical relativity. And this is a tough one, because I think the only code that can produce a large number of orbits is the SXS collaboration's code at pretty high precision. So this is a relatively old paper from 2015. I'm sorry I didn't update that off the archive. With 350 NR gravitational wave cycles, this mass just gives you a time scale, but you can scale it to any mass, so that's not important so much for a Q equals 7 system. So one black hole was 7 times the other. And then you switch to an EOB, that's effective one-body formalism, to keep it going and inspire. But what you want to do in this interim is with these super long numerical relativity waveforms, you can test PostAtonia as well and find out at what point PostAtonia is accurate to take over, and then when should numerical relativity take over. I don't know of a longer waveform to date. Did you guys produce anything longer since then?
That one was run by accident.
Oh, was it? Okay.
It was not intended to be that long.
Well, you made good use of it.
The student who set it up put the wrong initial conditions in.
How long does it take to notice?
You can see.
Oh my God. I need to sit down. That would have been my entire computing allocation, and someone would have been in big trouble.
It was orbital frequency versus gravitational-wave frequency.
Oh, wow. That's amazing. Okay, it's an even better story now. I was wondering, I'm like, where's your next waveform, guys? Come on, it's been a few years. All right, so this is what it looks like, but this is only for finite difference codes, but it gives you a flavor. So if this is too much, just close your eyes and forget about it. But the point is, we keep talking about, oh, it takes so long, why? The problem with any code like this is that we have black holes, and black holes are little buggers, right? Okay, they have infinite, they have singularities, You've got to resolve that or things blow up again. Thank you, Charlie Misner, but it's true. And so what we have to do are put grids that allow us to resolve that physics. But unlike some codes, like a cosmological simulation where you're doing dark matter halos, here we also have to get out gravitational radiation. So we can't get away with murder because we have to also resolve in the wave zone, which is where you're starting to look like a proper gravitational wave that's propagating out to infinity. And that's where we also have to have enough resolution. And that's what makes these codes harder to scale, especially the finite difference in codes. So I just threw some information in here to sort of satisfy my requirement to talk about computational challenges that was given to me. But it's not the same for every code. This is pretty consistent for any Einstein toolkit type of situation. Because it's amazing how many points you have to sit there on top of this black hole to resolve it. These take about 256. Back when I was a grad student, we were trying to use 4 points. I wonder why things were crashing. 4 points. Really ridiculous. So anyway, and then you need about 2M at wave extraction. So that's the type of scales we're trying to run. And you're talking about, you know, several million to 10 millions to more points across the grid when you run these codes. So for the numerical relativity codes, we are still not in the regime where you would say there's been a detection for LIGO because it happens so fast. Okay, let's go real time and get some more NR waveforms. That's a little hard. Lisa, I could imagine if you're starting to pick up years ahead, you actually could be in a situation where we would go target new simulations if we needed them for some reason, if something odd was happening. So that's just sort of a summary of that. So let's talk about these model waveforms for a second. Now, as far as I know, the IMR model waveforms, the one that cover in-spiral merger and ringdown, have all been tuned very heavily with LIGO in mind, and for good reason. LIGO's now and it needs it. So this might be maybe a future mock data challenge to test these in the LISA world. So what they are, they're a function that uses every bit of information we have. So we have PostAtonia, EOB, numerical relativity, all the physical parameters, and you do some fitting parameters and you get out a waveform that covers the full regime. Here we are again. And the reason you might want to do that is if you imagine if I just did numerical relativity in a spin of the black hole in the mass ratio space, I'd have these discrete points where I happen to do an NR waveform, but you want it to be a continuous space, and you want it, you want to be able to pick any of these parameters to build these waveform banks at which you do the match filtering that we just heard a little bit about. So the two major models, so this is kind of changing now, but the two major models that if you open up any of those LIGO papers for the detections of binary black holes, that you would see mentioned is the effective one body fitted to numerical relativity and the phenomenological models. So I have a slide on each one of them to sort of compare and contrast what they do. So the EOBNR waveform, this comes from Alessandra, uses post-Newtonian theory, then uses what Kurt was talking about, the effective one body. At the time when this was built, we couldn't do numerical relativity yet. We couldn't solve the two-body problem, so it's a very clever adaptation to sort of get around the part that we couldn't solve the two-body problem by treating it analytically as an effective one body. And then now it gets fit to numerical relativity. So you take some numerical relativity waveforms, and there's some free parameters in here, and you fit those parameters to successfully or faithfully reproduce the NR waveforms for a series of physical parameters. So this is what it looks like for one particular case that was, I think, published in 2007. So here's that post-Newtonian EOB in-spiral. Here's where the merger ringdown was, and they fit it together. And this is the gravitational waveform, and this is the frequency evolution. And so you can see here where they actually then have to do the fit between the merger ringdown and the in-spiral plunge. And there's been a lot of work on this, and there's many papers, which I have some of the most recent ones in a future slide. I put this down to remind myself to say it. One of the problems that has been is that there's actually quite a bit of physics in here, and these models are actually ODEs, or ordinary differential equations. You still have to solve them. So it's not necessarily fast, and so people have built surrogate models and other things to speed up this process for real time. The second competitive model are the phenomenological models. These typically are in frequency domain, although originally there was also a time domain one. I don't know if that's used as often anymore. These are hybrid models. They take post-Newtonian and numerical relativity and fit them together. So here you can see in this plot, here's the gravitational wave strain, here's the mass. This is the frequency, in units of mass. And so here we have region 1 is that in-spiral region. Here's the numerical relativity region and ringdown, and then in these regions they're doing the fit. Here you might fit to perturbation theory, and here PostAtonia. And so they are a pretty simple model for strain and frequency space with the parameters of the amplitude and the phase. So it's a pretty quick model, and a lot of work has also been done here. Both models have been very successful. What's been missing, at least from the LIGO point of view, has been the same as we were talking about the in-spiral waveforms. We're always trying to get as close to the reality of what we might have in the universe as possible. So we add precessing spins. So those spins, you start with what you can do first, which was non-spinning, and then you have the spins aligned, and then you let them precess, and all that adds complication to building not only the numerical relativity, because we have to solve the equations for each case, but also then building models that encompass it. High harmonics. So in the Emery case, we're talking about the same thing with these higher harmonics that go past the dominant quadrupole. But here, we will get them basically for any, as your binary system could orbit or could be off plane to where Lisa is. But we're also talking about from eccentricity, from mass ratio, from precessing spins, you distribute some of the energy into higher harmonics. So this is a new EOB model with precessing spins. This is a new model out of the phenomenological group that includes higher harmonics. There's some new models from neither group, actually, that now include eccentric models. So we have one from UNC out of Illinois and one from this group. And then, of course, I mentioned already the surrogate models where you speed up the way we can generate waveforms from numerical relativity. This plot I took out of the eccentric paper. Wait, or is this higher harmonics? This is the higher harmonics paper where they compare precessing numerical relativity with EOB and R, and you can start to see, oh yeah, it's this paper, my apologies. You can see how well now they can model a precessing binary. And so that means we can hopefully be able to detect these precessing spins out there in the universe. The second example I pulled from the eccentric paper. So if you look on this side, this is a new code called enigma. They're looking at what would be a quasi-circular waveform, and then what happens if it were eccentric, and you can see how different it looks. So they're building models so that we can capture all this modulation in the signal so we could, in principle, measure eccentricity. So this is where I think we are in terms of building models of waveforms that cover that in-spiral merger ringdown part of the thing. And a lot of progress has been made, especially very recently, but all of it's been done with LIGO in mind rather than Lisa. So that doesn't mean it won't apply. It just means it probably should be reassessed given the accuracy we might need for Lisa's waveforms. So here's what we were looking at. We were looking at in-spiral merger and ringdown. I wanted to just mention ringdown from this point of view rather than the Emery point of view. So this is the idea that after the two black holes merge, they settle down into a single black hole. And we tend to call that ringdown. And it's, as Kurt already mentioned, it's really beautiful because a single black hole is described by its final mass and spin. And what's fun about numerical relativity is numerical relativity basically provides you a map because from perturbation theory, you don't know which modes will get excited and you don't know their amplitudes. But when you collide the two black holes together, numerical relativity provides you all that information. And the hard part is waiting and being accurate enough to see this ringdown when you're completely described in this perturbation space by an exponentially damped sinusoid. So we have this in numerical relativity, but it's hard to get at because you have to have a very good waveform to see all that. And you can see the ringing of the bell. We usually describe this in sort of like introductory classes, that what's fun about a black hole is just like a bell. When a bell rings, the properties of the bell are what determines the frequency of that. And the same thing is true for a black hole. So the properties of the black hole itself will describe for you uniquely the radiation that's emitted. And so we usually think about this in terms of testing things like the no-hair theorem. So this is only a small section of just my group's waveforms. It's a pretty old plot. But I wanted to explain how that's one of the byproducts that we get out of this is we find these remnant black holes. And this is the final spin of the black hole in a weird expression in terms of the total mass radiated, or the final mass. You could look at it that way. And you get all this information. And what Kurt mentioned is that we were talking about how you can do tests of general relativity. And one of the things we do are consistency tests. And so numerical relativity can take the initial values of all these binaries, and there's been a lot of nice work on fitting formulas and tell you what final mass and spins you should get. So that's one of the things that is produced. And it's an opportunity. The hard part here is that I didn't include these slides for the sake of time, but that it's a little bit hard to detect an exponentially damped sinusoid and to get multiple modes. But something like Lisa, I think, has a real shot at it. I don't know if anyone's determined how many modes, depending on the total mass of the binary, you might be able to detect with ringdown. And of course, you could use perturbation-inspired waveforms to do this, but it's also very interesting to get at that nonlinear part when you go from the merger to the ringdown. It's an opportunity we have available. So really quickly with wet binaries, these are going to be, now what I'm saying right now might be a lie, but as far as I know, when we put these binary black holes in a wet environment, the gravitational waveform itself doesn't change, right? Because you have to add a lot of mass before you really start changing how the gravitational wave emission itself looks. In fact, if you create enough mass on individual black holes, you would do things like increase the rate of merger time, for example, and people see some of that. But you're not changing dramatically the gravitational wave emission, but what you are affecting is the electromagnetic emission, and finding a smoking gun that would say a merger of two black holes just produced that. And of course, Lisa, by detecting the merger of the black holes, would provide that smoking gun. There's a tremendous amount of work that's done looking at the environments of binary black holes. I collected a few here. And there's also a huge computational modeling challenge because you go from 10 to the 5th parsecs down to 10 to the minus 5th parsecs, right? I mean, it's incredible range. And so I have just a few slides that talks about where we are in terms of wet binaries and how we might know the electromagnetic signatures that will accompany our supermassive black hole mergers. So in the circumbinary disk problem, there's sort of 3 phases that are looked at, and people look to study whether or not they can find electromagnetic signatures from these 3 phases. So there's a predecoupling phase when the disk is viscous. So you can think about this disk here. The 2 black holes are in the middle, and there's an accretion disk around it. And this is during the part where you have a quasi-equilibrium state, and there's very slow in spiral. Then you have this phase where, I think that was relaxes, my apologies, where the viscous is still larger, the gravitational wave, and the binary decouples from the disk. So now the binary exists independent of the disk. And then you have your post-merger of your black holes, often called afterglow, and the disk fills the hollow left behind by these black holes because they've merged, and you see an accretion ramp up. So that's sort of the introductory state of what can happen. And this is sort of, this looks crazy, right? Here's a sum of all the work, not all of the work, but some of the work that's been happening. And it's incredible. So you went all the way from analytic and PostAtonia models that looked at this to full GR solutions with thick disks. And the key thing here is to look for reliable signatures, because as you add more and more physics on, you want to know what is consistently holding up that we might be able to search for in the universe. So people have been looking for jets forming and signatures of the black holes merging and many, many things. So I just added this so people could, at their leisure, on your plane rides, read some great papers. So I picked a couple just to explain what's been happening. Here's one from, I think the only time my group almost competed in time was Stu Shapiro. I always have to look up what Shapiro's done before we publish anything, because usually he's already published it. But we were looking at supermassive black holes and hot gas, and what we were looking for was, would you ever detect the fact that a black hole has merged and you have a sudden drop-off of variability because you went from an in-spiraling situation to a single black hole? And this is Bremsstrahlung radiation in ergs per second. And the problem is it would be hard to imagine pulling out this electromagnetic signature from inside something like an active galactic nuclei. People have also looked at magnetic fields surrounding these black holes. A lot of work on this, looking for jet formation, and also looking for how we might detect that radiation. Here's the electromagnetic versus the gravitational wave emission in ergs per second and in time, how quickly that would ramp up and decay. Again, this emission doesn't look likely to be seen directly, but you might get it from understanding black hole accretion rate. So here's another example of work that's been happening. The most recent work I found was out of Shapiro's group on transient signals, distinguishing single supermassive black holes from supermassive black hole binaries. So they want to see that, can you tell whether or not it's just a single supermassive black hole out there accreting, or there's a binary in the middle? And he's been studying 3 different scenarios of what the disk looks like, the accretion disk around the 2 black holes, to see if it's robust. And he finds robust situations where he gets similar signals out of all 3. And you can see here, this is the green represents the velocities, and the white are the magnetic fields. So here's a good picture of the 2 black holes with the magnetic fields threading through, and you can see the jet form at the end. So that's probably the most recent work on wet binaries that came out just a few weeks ago.
Almost right.
This is it. So here's your state of the art of your wet binaries, looking for electromagnetic signatures that the aftermath seems stronger, so after the merger rather than before at the moment, from what models can tell. They're still, I wouldn't call them in their infancy, but there's still a lot of work because there's just so much physics that you have to add and figure out which part of the physics was really necessary to get robust signatures. And here, as was required, hoops and directions. So I added what I thought was the most exciting bit from the L3. How, when, and where go the first massive black holes, form, grow, and assemble, and what is the connection from galaxy formation? This is what we're after. What is the nature of gravity near the horizons of black holes and on cosmological scales? So a really noble pursuit, I think, the physics of what LISA can give us. I think the key for this subject is that we need waveforms of certain precision over the relevant parameters. And I put baseline because you have these threshold binaries. You should have a minimum of what you want to achieve. We have to make sure we get it. Put a cautionary tale personally from LIGO, because I think we were not really expecting the IMR waveform to be so important for the first few detections. So people had to ramp up and make sure we were ready. And considering that we still have time with LISA, we don't only want to be able to do the physics we expect to do, but be in position to do all the physics we could do. And we already talked a little bit about these alternate theories. And here's my own hope for the workshop. I'm hoping that someone knows what amplitude, phase, and maybe eccentricity errors, how precise we need to be on waveforms based on all those threshold binaries we have for each of our objectives, so that we know what our target is. So for example, to prove the existence of an intermediate mass black hole binary, you need to detect a certain range, and you need the lightest black hole to be an intermediate mass black hole, and that puts a requirement on the precision that you want to be able to measure a component mass. And I would like to know that we figure out what this means in terms of the waveform amplitude and phase that we compare it to. So that's just my own little personal hope. Thank you.